I'm Chris Brooks, and today I'll be talking about Kepler's three laws. Now, his first law is that all planets will orbit the Sun in an elliptical orbit, with the Sun at one of the foci. Let's choose left foci as the Sun. Now, the this law is sort of intuitive with the fact that the only force acting upon the um, planet is that of gravity, and it's always pointing towards the Sun. And as such, the only possible the only possible shape for the orbit is either an ellipse or a circle. And a circle is just a very special ellipse, both foci at the same point. So let's get rid of these arrows, and we can move on to the second law. And the second law is that uh, at during equal time intervals, and these lines are pointing to where the planet would be at certain times. So this would be time 1 and time 2, so that's delta T, another time 1, another time 2, delta T, and if I drew these correctly, these delta T's would be the same, and another time 1, and another time 2, and it again, delta T, that the line from the Sun to the planet will sweep out the same area in the same amount of time. And this is sometimes called Kepler's pizza, especially by people in Askey's physics class. Now, this can be proved with the fact that you take calculus right triangle, the area of in a very small amount of time of delta t will be ds, the very small amount traveled, and r, the radius at which it travels at. A very small area that it travels is equal to ds, r times ds over 2. And then we can divide both sides by dt, and you get the r times ds over 2 times dt. You get r per v, since the ds is always perpendicular to the r, over 2 is equal to the change in area over the change in time. Now, the r per v, you multiply that by n, so it's m times r per v. That gives you the angular momentum. Now, dividing by 2 times the mass, you get, oops, I need to cross out the 2, you get the same equation that we got for dA dt. And the angular momentum, since the forces are all acting towards where we're measuring it about, the Sun, is constant because there's no torque from the gravity. And that is Kepler's second law. Now let's move on to his third law, and his third law simply states that the that the time that it takes for a planet to move all the way around in orbit, that squared is proportional to the semi-major axis of the ellipse cubed. And the semi-major major axis is the one that goes through both foci. Semi-major axis is just the distance, is just half that distance. That's it. But for now, the easiest way to prove this is simply through assuming that it's mostly circular. And actually, I'll put a link below in the description that shows a way to prove it, even if you're taking into account that it's elliptical, and proves that it is only with the semi-major axis. But for if it's mostly circular, then your centripetal acceleration, which this is not this A is not that same A. For this, we're taking that A is R. Centripetal acceleration is equal to omega squared times R. But that's also equal to, since gravity is the only force acting, is equal to universal gravitational constant times the mass of, in this case, the sun, times the mass of the planet, divided by the radius squared, and also divided by the mass of the planet, in which the mass of the planet cancels, showing that it doesn't really matter what the mass of the planet is, so long as you know what the radius is and what the mass of whatever it's orbiting about, in this case the sun, which is that big. Now, rearranging this a bit, you get, or multiplying by r squared, you get omega squared r cubed equals g times the mass of the sun. Now, omega is equal to 2 pi times the frequency, and the frequency is equal to 1 over the period of the planet's orbit, which is the TP. So omega equals 2 pi over TP. So means that plugging into here, we get 4 pi squared over TP squared times radius cubed equals g times m. Now, this almost looks like the second law equation, or third law equation that we got. We just need to multiply by tp squared and divide by gm. So get tp squared equals 4 pi squared over g n times r cubed. Now, this term right here is often just stated as some sort of constant, and for the sun, it is equal to 1 year squared per astronomical unit cubed. And this comes in handy when you're working problems and you're given something like the comet's period is this long and it gets this close to the sun, and then figure out how far it is away from the sun it is at its furthest point. And I'll be back with some examples.